Thank you very much for giving me a chance to speak here, and thank you for staying here while we're waiting for the, I mean, I'm the only thing that's separating you from lunch right now, so thank you for giving me this time. Now, the co-authors and the title is there, so I will jump right into the story. So this is really about, to give this talk, I have to start with a review of an old story. So here's some old story. This talk will mostly happen on the Blackboard, and the slides are just auxiliary. So suppose that I'm in the ADS-free CFT2 setup, and suppose that I'm on an equal time slice, so that, in fact, I will never have to draw this cylinder anymore. Yeah?
Can you,
yeah, let's project the Blackboard. The slides are not important until they become important later. So for now, we're doing that, yes. So here's an equal time slice of this geometry, and suppose that I have a curve in the bulk. For example, this, and I would like to compute the length of this curve. And the only thing I know, because this is the workshop where we are, is the Ryu-Takayanagi proposal. So the only tool that I have at my disposal is geodesics, because minimal surfaces in this dimension are geodesics. And so the one way that I can, or really the only way that I can proceed, is I can try to describe the shape of this curve for a set of tangent geodesics. And just to set some notation for the future, every one of these tangent geodesics, I will call the left endpoint of it U and the right endpoint of it V. And the fact that I have tangency is going to be tangency to the curve is specified by the condition that, let's say, U is equal to U of V. There is some functional dependence between them which says when my geodesics are tangent. And so I'm interested in computing the length of the blue curve. Let me write it as length in blue so we all know what we're talking about. And because I'm using the Ryu-Takayanagi formula, the lengths will be related to entropies through a factor of 4g Newton. So let me just set 4g Newton to 1, so I never have to write it again. And with that assumption, here is a formula for the length. It's an integral over v. You go all the way around, and the integrand is the following partial derivative of v, where u is the tangent geodesics. And this is called the differential entropy formula. And I had the pleasure of collaborating with Jan and Michał and two other people who are not here, but one of them should be, and that's Vijay, on first writing a paper about this formula. Then there was also work by Rob Myers and Matt Hedrick that further developed this idea. So this is what's called differential entropy. And the title of the talk, which was displayed a moment ago, was two-sided Crofton formula. I probably should have given the title two-sided differential entropy and two-sided Crofton formula. That would have been a better title. So this is half of what I want to talk to you about. Then there's the other half. So it turns out that this formula, so now on to the Crofton formula. So it turns out that this formula is subject to some very nice rewriting. And the nice rewriting is like this. So for this, I have to introduce a new ingredient, and the new ingredient will be called kinematic space. Yeah. Here I haven't made any, well, static in free bulk dimensions is the only assumption that I have made so far. I guess there is a question about what to do when the topology of the spatial slice is complicated, and that's kind of what my talk is about. So right now I just imagined I'm on a circle on the boundary, and we'll go away from that. That's precisely the point. So now kinematic space. It's a two-dimensional space where these two things are identified. So it's a piece of cylinder, and the size of the cylinder in the horizontal direction is 2 pi, and the size of the cylinder in the vertical direction is pi. And I want to introduce two coordinates on it. And those coordinates are precisely u and v, which are the same u and v as here. And so the coordinates in that space are the endpoints of these geodesics. In other words, if I give you 1 point over there, then that 1 point corresponds to, that means giving you a value of u and giving you a value of u, that gives you one geodesic. So this point here has some coordinates u and v. It fixes these two things, therefore it fixes this geodesic, yes? And so kinematic space for our purposes right now is the space of oriented geodesics. I said oriented geodesics because I distinguished the left endpoint from the right endpoint, yes? So everyone with me so far? Okay, so now let's talk about this function u of v. This function u of v is some function in this space, so I could just plot what it is here, yes? There's some place where u is equal to u of v, and that's the set of geodesics which are tangent to my curve, correct? But there's more than one of them. There's also the other one, because this is the space of oriented geodesics, and on this curve, I have oriented my geodesics in such a way that the interval that they subtend, this interval, is just like outside, or its entanglement wedge is outside the curve. Now, if I go upside down and I call this u and this v, so that the oriented interval is this one, then I will still have a tangent geodesic, but it's tangent from the other side. It encompasses the curve, the entanglement wedge, rather than just touching it, yes? So there is another curve here, which we can try to write a function, a description for it. It would involve the inverse function of u. I'm not gonna bother writing it, but there is some other curve here, yes? Okay, so now let's look at this picture. Okay, and clearly this formula, the differential entropy formula, is an integral over one of these curves, yes? Well, it's an integral over this one, but it's also an integral over this one if you go in the other direction. So that's a significant fact. When I look at this formula for length, and when I look at this picture, I realize that this formula here on these tangent geodesics, yes, it localizes on the boundary of a two-dimensional region here, yes? And so I should be able to use Stokes' theorem to rewrite this formula as a volume integral over this space over here. So let me just do that. And the outcome is that this is equal to 1/2 of an integral du dv of the exterior derivative of this thing, which is just d second uv du dv. Now, why is there 1/2? Because this region has two boundaries, and each of them can evaluates to the differential entropy. And so this formula here is what's called the Crofton formula. Crofton was an Irish mathematician in the 1860s who first had the idea of describing lengths of curves through their intersections with planes, I guess. And that's what we're doing here. So the interesting thing next that I would like to remind you of, this is a story from 10 years ago, so many of you have seen it, but we need it for this talk. What is the region of integration? Well, the region of integration is here, yes? But with reference to this picture, what is the region of integration? Well, here is an example of a point which lives just on the, which is just tangent to the curve. Here is an example of a geodesic which is oriented this way, which lives over here, yes? What lives in between? It's geodesics that somehow interpolate between this one and that one. And all of them have a feature that they intersect the curve, yes? So the interior region between one locus of tangency and the other locus of tangency is the region of intersection, yes? The boundary of intersection is tangency. And so here I can just say that this is an integral over intersecting geodesics. Okay, and there's one more thing I wanted to say, which is that since we are taking an integral over intersecting geodesics, then let's think about the form or the measure with which we are taking this integral. I'm going to call it d geodesics, because we're really taking an integral over the space of oriented geodesics. Let's think about what this d geodesics is. And the statement, the first statement to make here is that d geodesics everywhere is a non-negative, is a non-vanishing form. And why is that true? Well, if we look at the form of this geodesic, we realize, let me discretize this. So let me make these little du's finite. And then what will happen is that I'm really talking about some u and du and v plus dv. And this expression that we have over here is basically the length of this geodesic plus the length of this geodesic minus the length of this one and minus the length of that one. Yes, these are with negative signs, and that's with positive signs. Yes. Now, if I call this thing B, A, and C, then this is equal to this measure, yes, is equal to SAB plus SBC minus S of B and minus S of ABC. And I realized that this is a conditional mutual information, and that's non-negative by strong subadditivity. Okay. So this is the review, and I just finished the review. And now are there any questions about the review? And if not, then we will move on to the new stuff.
I guess this can be generalized to higher dimensions where you have surfaces and...
Not easily. There are some papers on the generalization, a paper by Vijay and I'm blanking out on the name. A student from UBC who was a postdoc at Penn, huh? Charles Rabido. That's one example of a generalization, but not straightforwardly. Okay, any other questions or comments? If you, the cases that are straightforward are the cases that are secretly like this dimension, but you just have some trivial extra dimensions. But modulo that, as soon as you go to an honestly higher dimensional setup, then it's not straightforward. So we have this story. Any other questions or comments? And thank you very much for these questions. Ronak seems to have a question. Oh yes, you can generalize it in. So yeah, I can give you a reference later on how to generalize it. It's I wrote a paper with one of my students about how to do it. Yeah, that won't play a role for today's talk, but a generalization exists. Any other questions or comments? Okay, so I'm going to put a big star over here in this step, because this step is not something that we can do in general. And so a big part of this talk is about trying to remove this star and actually understand what to do when the obstruction doesn't happen. So what's the obstruction? We suppose that over here, there was inside it, a black hole with some horizon. In other words, suppose that this state was not a pure state, but a mixed state, and there was some horizon in the middle. Well, then I would have wanted to do this step and say, oh, I'm just going to go do an integral over these intersecting geodesics. But I no longer can just go ahead and deform this geodesic to that geodesic. I mean, this geodesic exists, but after that, I will start getting geodesics that look like that. It's a very different story. And so it seems like I was only able to do the Stokes' theorem because there was no black hole horizon. Yeah. Okay, yes, that's true. But however, then if we believe Takayanagi, then there would be a smooth way of going with the minimal surface from one end to the other end. Yes, so. Well, that's definitely here. I assume staticity. I'm not sure. I mean, staticness or whatever the right word is. Yeah. So anyway, I would have said that if I have a pure state, then there is a smooth way of deforming the Takayanagi geodesic from there to there, because there was any obstruction would have been due to the fact that the state is mixed, I think. Yeah, then the story becomes significantly more complicated. This is not the direction where I want to go in this talk, so we can have that conversation afterwards, but that's not something that I want to dwell on in this talk. Okay, so is everyone clear on why I put a star here and why this is why this step has a problem. Okay, so in the remaining half an hour, I'm going to tell you about how to fix this problem. And there will be a new differential entropy formula, and there will be a new Crofton formula, and this thing will work for two-sided work in a two-sided way, and it doesn't have a problem with horizons. And so that's where we are going next. So before we go on, I'm going to march all the way to the other side of the board and rewrite this expression in a way that looks like a tactical retreat, which is that I'm going to assume that formula is obviously continuous, but I'm going to imagine that there is a, just to make it look similar to the previous picture, here's a curve. I'm going to take that formula at some discretization level and not in the continuous form. So suppose that here is one of my tangent geodesics, but here is another, and here is another, and I'm treating seriously the fact that there is a discrete family of these things. Now, these are the terms that have positive coefficients here, but the formula asks me to integrate over the partial derivative with respect to one endpoint, yes? And so really what I'm doing is taking this geodesic minus this one minus that one, this one minus that one. Does that make sense? And so I also have these negative terms, and the negative terms have a structure which looks like this. Does that make sense? So does everyone agree that this is a discretization of the formula that I have over there? So I'm going to call these basic regions A1, A2, A3, and so on, the things that make a difference between being an overlap and not being an overlap of two geodesics that I'm taking. And if I do this, then if I do this, then I will have the following picture. I will say that this expression that we wrote over there looks like the entropy of, let's say, A1, A2 up to some AK minus the entropy of A2, A3 up to the same AK. So I just chopped one from the beginning. And then there's a next term which looks like A2, A3, AK plus 1 minus A3, A4 up to AK plus 1, and so on. Does everyone agree that this is a discretization of the formula that we wrote over there? I want to hear a yes or no, because I really don't want, if you miss that, then you don't. We're taking a, What is K? K is so here is my little region A1, A2, A3, but the geodesic that I am taking doesn't just encompass one region, it encompasses some number of them. And so that's measured by K. Okay, am I taking 3 regions at a time, or 4, or 5, or some number, yes? And the point is that I take the entropy for my number of regions. That's the thing that makes me tangent to the curve. But then I'm taking a derivative, so I'm subtracting the thing which would have wanted to be infinitesimally smaller. But I'm doing it discretely, so I'm making it minimally smaller as allowed by my discreteness. That means I'm just removing A1 from it. And then I keep going, and the sum is like integrating over there. Well, yeah, every region is separated by K. Yeah.
You're still computing the full length?
I'm computing a discretization of the length. So if I take a limit where I have infinitely many infinitesimally small intervals, then that formula will become that one. This is a discretization of the right formula.
Whatever this formula will give you will not exactly be that.
Yes, but there's some total number of regions, A1, A2 through AM. There's a total number of regions, M total. And the idea is that the limit as M goes to infinity of this thing will be that thing.
And all these intervals, discretizations, boundary intervals have the same size.
They don't have to, but the sizes are somewhat related to what curve I'm talking about.
When you take derivative this way, you want to divide by some epsilon, so you do want that epsilon.
Well, again, this is a discretization, so I'm not really taking a derivative. It will only become a derivative in the limit. Right now, I'm just doing some coarse approximation. I see that I'm getting some resistance on this formula, and I have to say that I expected that this is the smoothest part of the talk. So you're surprising me with your resistance. Huh?
The discretization would be okay, but if you discretize at uneven intervals, then I'm a little worried, right? You might worry about what.
That's the uneven intervals are the information about that is sitting in this function u of v. Yes, like this u of v is not constant. It can go up and down. So that tells me that sometimes I'm adjoining a bigger interval and sometimes I'm adjoining a smaller interval. That which in turn reflects the shape of the curve. Yes. Yeah, well, this is like a Riemann sum. This is, or maybe I should have said it this way. This is the Riemann sum for that integral. If you now imagine that you plot this partial derivative there, what would you write if you were writing a Riemann sum? You would write this. And then, with, not necessarily with equal intervals. You can also have unequal intervals, and that's also a Riemann sum. It's not a standard Riemann sum, but it's also one.
Kind of bordering this smooth curve, but it has these the edges.
Is there a question there, or is it a comment?
Yeah, I'm asking whether this this sum is actually exactly equal to the length of a curve, closed curve, which is not smooth, but it has these.
No, the sum is not equal to the length of the curve.
Not this curve, but a curve which is outside this.
We literally see what the sum is. The sum is this geodesic minus this geodesic minus that one, this one minus that one. I drew for you what the sum is.
Okay.
This is the sum.
Yeah,
and the statement is that if I make this infinitesimally spaced, then those green curves will link up to the white curves, and there will be only an infinitesimal difference, which will become the length of the curve. So that's the non-trivial part of the claim, which was established 10 years ago. And so I won't prove to you the statement, but that's the statement. Okay, great. So it seems like, yeah.
I kind of sympathize with Surat's point. It feels like this is partial derivative with respect to v, right? But we are somehow tuning u also accordingly. Because your discretization is completely dependent on what you have.
I think.
That you have before.
Okay, so I think at this point, I'm going to cut this discussion, and I will say we are going to do it after the talk offline. The statement is definitely true, but it will take us really far afield to try to establish this. And this is I want to focus on other things. So for now, believe me, and then we'll talk about it afterwards. Okay, so that's that. And I would like to establish, now that I have these things written up here, I would like to establish a little bit of notation for this thing. So this thing is going to be called so I want to make two assumptions now. The first assumption is this M total is an odd number, okay? I will want to recover that formula, I have to take it to infinity. There's no trouble taking M odd to infinity, so that's okay, yes? So the first thing is that I will assume that this M is odd, yes? Now a little piece of notation. When I look at this term, I have K of these things, yes? I'm going to call this A1 K. 1 tells me where I start, and K tells me the length, yes? So this is A1 K. This here is A2 K minus 1. This here is A2 K. This here is A3 K minus 1. Is the notation clear? Okay. So then I would like to write so let's write this out as a sum. So there is a sum over I of the entropy of AI K minus the sum over I entropy of AI K minus 1. And that is supposed to be this discretization of the curve, yes? Now the statement is that as I take M to infinity, this thing will become the length of the curve, but it will approach the length of the curve from above. So at every intermediate step, I have something which is actually greater than the length of the curve. And now I want to go to where our problem with the star went, yes? So the obstruction to taking the key step over there and using Stokes' theorem was that maybe there is a horizon over here, correct? So this here would be, huh? Well, I'm not asking you to understand it. I'm just informing you. We can talk about it later, but I'm informing you that that's the case. So, so suppose that I have the horizon of I had some black hole here with a horizon. Okay, then the statement is that I just wrote this formula for you, which is supposed to be an upper approximation, so an approximation for from above for the length of the curve. But that curve itself is definitely greater than the entropy of the black hole. Yes. What is the entropy of the black hole from the viewpoint of my discretization? It is the entropy of A1, A2, all the way to AM, correct? And clearly, the length itself is larger than the horizon. So therefore, this thing is the upper approximation also is greater than the horizon. Does everyone agree with the thing that I just wrote so far? Yes, modulo Suvrat's question. Yeah, Abhijit. Huh? 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 Sorry, what's the question? This is k minus 1. These are the shorter ones. Yeah. Do you agree that these terms will all be AI k minus 1? Do you want me to write plus 1 here? But it's the same sum. I'm summing over all of them. But it's the same sum. Where I'm summing over all of them. Okay. Yeah. I am assuming that the curve wraps around the horizon, indeed. No, not here. So we'll, no, so far no. I'm talking about a curve that looks like this. I place the black hole in the middle here. Okay, very good. So I have this formula, and now I said that I was going to make two assumptions. So the first assumption is that M is odd. Now I'm making a second assumption, which is that K is equal to M plus 1 over 2, which is the smallest possible majority of these regions, yes? And for that special case, when K is equal to M plus 1 over 2, that's why M odd was very nice for me, I'm going to change my notation, and I'm call it A1 plus, and this one will be A2 minus. A2 plus and A3 minus. So plus and minus just means taking M plus 1 over 2 for K, and then here I had K minus 1, that's M minus 1 over 2. I'm using the simplified notation just for that case. Is that okay with everybody? M is the total number of regions. I discretized it, and I have maybe 101 regions, okay? Some number of regions on the boundary. K is an independent parameter, and I'm setting it. I'm not saying that K, K is not immediately related to M. I am choosing a special value of K. Choosing a special value of K means choosing a curve which is sufficiently small, yes? Okay. Huh? I'm choosing a curve. Yeah, by setting this, I'm choosing my curve. So this is A plus, and this is A minus now. Is that okay? Okay, good. So now let's just to develop an intuition for it. Oh, yeah. Which bound? Sorry, this one? It doesn't care about the black hole. It cares about how closely this curve wraps the black hole. Because if I chose K smaller, then I would be doing things like this. If I choose K larger, then my geodesics are like that. So they just get closer to the black hole. So choosing K that is just means that I'm taking the curve, which is sort of as close to the black hole as possible. Okay, any other questions or comments? Okay, very good. So let's just develop some intuition for what this is. I said that M is equal to 3. I said is odd. So let's take M equals 3, just to warm up. So I have 3 regions, A1, A2, A3, correct? And A1 plus is A1, A2, and A1 minus is just A1 itself, as an example. So now let me write down this sum. And just to bring things in a form that is more easily recognizable, I'm putting this on the other side, yes. Okay, it's still the same inequality. So what this looks like is, I will stop writing these S's because it just wastes my time. The answer is that this inequality becomes A1, A2 plus A2, A3 plus A3, A1 is greater than or equal to A1 plus A2 plus A3 plus that term, which is the black hole entropy, which is A1, A2, A3. Does everyone agree that this is a special case of this inequality when m equals 3? Have we seen this before? This is the monogamy of mutual information, yes? And so the monogamy of mutual information is the first step in a discretization process that ends with the actual curve over there. Okay, any questions or comments about what I said so far? Oh my God, I'm doing really terribly on time. You guys asked too many questions. So yeah, Sumit.
So where was the input that the blue curve was completely closed in the back?
Oh, it's in the fact that if it wasn't imposing, then some of these tangent geodesics, like they wouldn't be, like suppose that I was trying to describe all the tangent geodesics, they would start to have to wrap the black hole. Yeah, and I disallowed that. Okay, any other questions or comments? Sorry, the thing that about too many questions was a joke, so do ask questions. So fine. So now we're going to take input from, I would like to go back to slides now, so please turn on the slides. So I have been doing a lot of work about the holographic entropy cone, which is about relations on our necessary conditions for entropies to be satisfied if they are consistent with the Takayanagi proposal. And I gave a talk, which was an hour and a half long, where I in detail described a new family of inequalities that my students and I discovered. It turns out that removing the star there is going to happen by using those inequalities. So let me walk you through this logic. So here are all the entropy inequalities that people knew up to a year ago. By now we know more, but up to a year ago, this was a complete list. And I would like to point out these two inequalities. The first one there is the monogamy of mutual information. That's exactly this guy. What is the second one over there? It is the same thing for m equals 5. The next odd value over here, yes? And so going through this process allows you to discover, I mean, you could have discovered, no, you could have guessed that inequalities like that are true. Now, going through this argument doesn't guarantee that those inequalities are true, because these inequalities are meant to be more powerful. They're supposed to be obeyed by all holographic states, not just like a set of intervals on a circle, yes? But somehow that picture there motivated these inequalities, and then we could have checked if they are true more generally, and they happen to be true, okay? So, so what's our method for generalizing for removing the star over there? Well, it turns out that there is my students and I discovered a further generalization of these inequalities, which I will tell you about right now. So, sorry for switching back and forth, but we need the blackboard again. And I just want to say, if we have let me explain the generalization. If we have this black hole over here, then the total pure state that we are talking about is all of these A's together, yes? And then there is some purifier over here, which I might as well call B for black hole, but it's just some other region, yes? And all of these inequalities assumed that B had no structure. It was just one B, and we never even wrote it, yes? The inequality looks like this, and there is no B, yeah? So now I would like you to imagine with me a setup where on the other side of this geometry, there is a second side. And that second side looks just like this, and the purifier B is also subdivided in little regions, B1, B2, B3, just like this one. Can you picture that? So there is also a circle on the other side, and that circle from the other side has some B1, B2, B3, and so on. There is also some number of B's, just like there's some number of A's on the two sides. And the number of B's is, I'm going to call it N, and this N, I will also assume that it's odd. Yeah.
But from the other side, the curve is behind.
Yeah, that's from behind the horizon. That's right. Yeah, so I'm taking the pure, I'm saying, let me describe the whole pure state, including the other side, and I also want to describe divide the other side into little regions just like this one here. Okay, so imagine that you had a bunch of these regions B. Then I want to tell you that the following equality is also true, because I introduced the B's, yes? B1, B2, B3. Bj minus Bj minus, and I sum over both I and j. This is the modification. And it turns out that this inequality is also true. And let me just ask you, if you haven't seen this before, I suggest that you should be impressed that there is such a generalization. Let's see if this makes sense. So I said that B is odd, yes? The smallest value the smallest odd value is n equals 1, yes? Now, in my notation, plus means that I'm taking just more than half of an odd number, and minus means just less than half. What is just less than half of 1? 0, so it's the empty set. So if I set n equal to 1, then those bj minuses are empty sets, and that's why we never wrote them before. So the previous family of inequalities was this family when I set n equal to 1. But now, let's set n to higher numbers, and now we have a new set of inequalities there. So now I want to go back to the slides. Sorry about going back and forth. And so last time I said, where the inequalities that we just motivated with n equals 1 are the ones that are circled in red. It turns out that this blue one here, is the first inequality that doesn't have n equal to 1, but it actually sets n equal to 3. And so that's the first thing that it really, where this B really comes to life. And then the next one below that, I should have circled that, is when m equals 5 and m equals 3. So it's the next one. So more things here actually belong to this family. Now, when we took a sum over I, we were going around this circle, yes? When we take the sum over j, we're taking the sum over the circle that lives on the other side of the two-sided geometry, correct? And so we really, this sum, if I go back to an integral, if I take the continuum limit of this to try to recover back something like I had over there, then I would have an integral over one circle and over another circle. These are independent circles, so together, this inequality naturally likes to live on a torus. And this is why those inequalities are called toric inequalities. And so this is their general form. It's the same thing that I have over here. They're toric inequalities. Just as a sideline, we also discovered a family of inequalities which are related to the projective plane. It's not obvious that this inequality relates to the projective plane the same way that this one does to the torus, but that in fact is a true statement. Okay. But anyway, today we focus on these ones, and I just want to say that they have some very interesting structure. Well, here is another example. So here's an explicit example of what such inequalities would look like. So now I need to say a few more words about their structure, and then we will be able to fill in the blank for this missing step over there with the star. So there is I talked about it 2 weeks ago, but many of you weren't here, so I will briefly recap this. These inequalities, yeah. Well, the thing is that I can take this inequality regardless of where the regions A and B live, and it will still be true. But it will have, but it has a nice interpretation in terms of computing something if I put the A regions on one side and B regions on the other side. So it's, if I want to recover a nice interpretation, then I would put them there. But otherwise, the inequality is still true. And what's the proof that so yeah, we can talk about how to prove it. Like I talked about how to prove it 2 weeks ago a little bit, and I definitely will tell you offline. But the proof is, I don't want to overstate the case, but it's extremely complex and really relies on the fact that this torus is a torus. So, okay, but anyway, so we have these terms which live in the positive side and on the negative side. And then I have arranged these terms into a tessellation of the torus. I mean, we have a torus, we might as well populate it with something. where the regions that live on the greater than side of the inequality are faces, and the regions that live on the smaller than side of inequality are vertices, yes? So here is a graph where all the terms here, except for this special term, this is the black hole term, yes? Other than the black hole term, all terms have been cast as vertices and faces of a tessellation of the torus. The next thing to say is that, how do I know which vertex is incident to which face? The answer is that they are incident if and only if they do not cross. In other words, one contains the other, or they have no intersection. In other words, we have incident vertices if we do not have this situation. Sorry, that's not how I should have said it. They are incident to each other if one region contains the other, or if they have no intersection. And that condition this is what we call no crossing condition. This condition is very special because this is the premise of the entanglement wedge nesting theorem. We know that entanglement wedges nest. In other words, this situation never occurs. But to talk about this, I have to say, oh, some x is part of some y, and then I can exclude this scenario. So the premise for the assumption in the entanglement wedge nesting theorem is exactly the condition where I put a vertex next to a given face. Does that make sense? Okay, so now the next thing to say is that edges of this graph are little pieces of little conditional mutual informations. So I highlighted a single edge, and on this edge, you can write down the terms, the positive terms, so the faces next to this edge, and then the negative terms, so the vertices next to this face, and they make this combination. But I remember that my whole state is pure, so I can flip some of these entropies to their complements. They're equal entropies if I'm talking about a global pure state. And then I will rewrite this edge in this form. And when I do so, then I discover that this is just a conditional mutual information. So clearly adding up all the edges will add up all the things in this tessellation. And so I'm led to the conclusion that the entire inequality takes the form a bunch of conditional mutual informations is greater than or equal to the entropy of the black hole. This is going to be our Crofton formula. Why is this going to be our Crofton formula? Let's look at what the Crofton formula looked over here. I had an integral over this, and these things were what? They were all conditional mutual informations, yes? So this formula realized the length of the curve as a combination of conditional mutual informations. I'm trying to say that now we have this inequality, which is also a combination of conditional mutual informations. And just like that formula, it also bounds from above the entropy of the full black hole. But now we're doing it in a two-sided context. Any questions or comments about what I just said? Okay, so the next thing to say is that I would like to, so I have 2 minutes only, and clearly the Blackboard format is, and 40 minutes was not the ideal choice. So I'm just going to tell you about what happens when you actually derive this differential entropy formula in detail. And a lot of fun things happen. So it turns out that on the previous slide, we learned that all of these edges are conditional mutual informations. And now an interesting statement is that almost all of these edges, all of these conditional mutual informations generically vanish. Why do they generically vanish? Well, if I write down a formula like this one, which discretizes this which takes the continuum limit of these conditional mutual informations, then this formula looks like this. I have a two-sided black hole setup, yes, and I have some interval over here, whose endpoints I will call UA and VA, and I have some other interval over here, whose endpoints I'm going to call UB and VB. And does that make sense? So now, with reference to this picture, when I take the continuum limit of the formula that just disappeared from our screen, then the Crofton formula that you get looks like this. There is still a 1/2 like before, and I'm still taking an integral over du dv. I'm still taking a second partial of the entanglement entropy with respect to a u and a v. But I have these indices, UA and UB now. So the right combination turns out to be UA, VB. UA, VA, and UB, VB. Now, if you look at this formula and take a moment's thought, then you will discover that this second partial is 0 in every phase of in which this Takayanagi surface can be. So let's talk about the phases. Here is an interval, and here is an interval. So I will just talk for like 3 more minutes. Yes. So what are the possible phases for this thing? Well, one phase is if I sort of go the near way around over here. This is one choice of a Takayanagi surface for a union of such 2 intervals, the kind of thing that sits here. The other option, which I will draw in green, is if I go sort of the other side. How to draw it? So this is a circle, and I can take a geodesic which is just deformable into this interval, or the one that goes all the way around. And then I have the third option, which is the connected option. I can connect this with that, and this is a third option for what my Takayanagi surface can be. So I know that it's going to be in one of these 3 options, the yellow one, the green one, and the blue one. And now think about what the entropies are in this thing. In the yellow phase, the entropy is a sum of something which depends on UA and VA, plus something that depends on UB and VB, correct? I hit it with this partial, I get 0. What about the green phase? In the green phase, I again have something which is the sum of something that depends on VA and UA, plus something that depends on VB and UB. That's the length of the green geodesic. Again, I hit it with this partial, I get 0. What about the blue thing? Now it's the sum of something that depends on UA and UB jointly, plus something that depends on VA and VB jointly. I hit it with this partial, I again get 0. So in every phase, individually, this thing vanishes. Isn't this a problem? Does that mean that all of these mutual informations are 0 and our whole thing is just equal to 0? No, because there is a catch. I'm taking a variation with respect to UA and VB. What if I took a variation and just taking that variation caused the phase to jump? Then the argument I just made wouldn't apply. And so the only way that this integrand can be non-zero is if UA, VA, UB, and VB are collectively chosen in such a way that we are just at the phase transition in the Takayanagi surface. Did everyone absorb this argument? Okay, so now I want to go back to the slides. Sorry about that. And in the next 1 minute, I'm going to tell you some fun facts. So what we have established over there with this argument is that what I have established so far is that if you imagine that this is a torus that you get for choosing m equals 5 and n equals 3. But imagine that you're like 1,000,001 times 1,000,001, yes? Okay, they have to be odd numbers, but some very large numbers. You have this very big torus and a bunch of squares on it. And then the question is, when does this expression, where does it get non-zero contributions? This argument here told you that generically, the contributions are always 0. So when do I have non-zero contributions? When the edge that I'm looking at is just at the phase transition. Imagine that you highlighted all of those edges that are just on the phase transition. Here is an example of how you can do that. It turns out that if you take one of the regions bigger than the other, then the edges that are on a phase transition precisely happen to be the ones that live here. That's just a fact that we can verify together later. And so what are the lessons from this example? The lesson is that, first of all, the integral, it's a 2-dimensional integral, but it generically localizes onto 1-dimensional loci, and the 1-dimensional locus is the locus of a phase transition. The next thing is that, well, okay, I took this special example. What does it actually evaluate to? You go through the computation, and you realize that this integral is precisely this. And so this is our differential entropy formula. The integral localizes onto a one-dimensional locus, and the one-dimensional locus becomes that thing. So this is our two-sided version of the differential entropy formula. It localizes to that when you go through the exercise. But it is at the same time a two-sided version of this formula because it's written as an integral of these conditional mutual informations. So this example here is just for a special case when I took one region to be much larger than the others. But here are general facts. If you get to choose the phases of these entanglement wedges in different ways, then the integral always localizes on non-intersecting loops. That's the first statement. The second statement is that those loops always mark regions of or loci of phase transitions. Now, among those loops, some of them could be contractible, but there is always at least one loop which is non-contractible on this torus. Now, moreover, if you have a loop which is non-contractible, it always has to be an integer combination of loops 1, 1, and 1 minus 1. And the 1, 1, and 1 minus 1 loops, respectively, evaluate to the differential entropy on the A side and the differential entropy on the B side. And so this integral always gives you, if you happen to have a loop like this, always gives you A times the differential entropy on the A side plus B times the differential entropy on the B side. And there are more facts of this type, but let me just end with some kind of motivational punchline, which is that these facts we could have gone through this exercise directly in the continuum. I could have written a formula like this if I was able to guess it, but it would have been exquisitely difficult to prove the statements that I have over here from directly in the continuum, especially this one, that there is always a loop which is non-trivially wrapped on the torus. I have no idea how I would prove it without first going to the discretized case and only then taking the continuum. So this is some interesting fact, because these loops reflect phase transitions. It's some interesting fact about a topological fact about where the phase transitions occur as I vary the sizes of these A and B type regions. And to really discover this fact, I have to go to the discretum. And so it suggests that there is some interesting topology which underlies the phase structure of these RT surfaces. And I think that there is more to be discovered in terms of how to interpret that fact, or maybe how to use it. And I have a fantasy that maybe we can use this fact. It's a non-trivial topological fact about phase transitions in RT surfaces. Maybe the fact that there is always a non-trivially wrapped loop, maybe we can somehow harness it for constructing holographic error correcting codes with certain properties. So with that question, I will stop. Thank you.